Welcome to Yatim Khana and Madrasa Anjuman Khairul Islam's Pune College of Arts, Science and Commerce, Camp Pune 1. Myself, Dr. Arif Tamboli, working as Associate Professor in the Department of Electronic Science. Today we are going to complete the topic which is called Schmitt trigger. So Schmitt trigger is also called as sine wave to square wave converter. Basically, there are two types of the Schmitt triggers, namely inverting Schmitt trigger and number two, non-inverting Schmitt trigger. I hope after this video, you will understand each and every concept about Schmitt trigger. Let us start from very basic of the electronic science because in Schmitt trigger, two basic electronic circuits are used. First circuit which is used basic circuit is potential divider circuit. So you can see here input voltage Vin is applied to the potential divider resistor R1 and R2. The junction of R1 and R2 is declared as output voltage and the equation for output voltage is equal to R1 is upper resistor, R2 is lower resistor. So lower resistor divided by upper plus lower into whatever Vin you are applying. Same diagram I have shown you here. Instead of battery symbol, we have taken it V in somewhat like this here and here the ground symbol. And junction of R1 and R2 is taken as a Vout. So voltage divider or potential divider circuit output voltage at this point means at the junction of R1 and R2 is given by formula Vout equal to R2 means lower resistor divided by R1 plus R2 that is upper plus lower into Vin. So this you remember it is very simple. Next block which we are using inside the Schmitt trigger is operational amplifier as a comparator. So all of you know that operational amplifier IC is shown by a triangle symbol along with two inputs, namely inverting input marked by negative sign and non-inverting input marked by positive sign. Plus VCC is the positive voltage supply, minus VE is the negative voltage supply. In case of op-amp 741, we always use plus 12 volt, minus 12 volt as a power supply. This is the output voltage of the op-amp. Now when op-amp is used as a comparator and that is true in open loop means output is not feedback to the input. So when op-amp is used as a comparator, at that time all of you know the basic. Once again we are going to revise it. Whenever voltage at non-inverting pin, that is positive pin, is greater than voltage at inverting pin, that is negative pin, the output voltage of the op-amp Vout is forced to go into high voltage level. So Vout is equal to HVL. So with reference to your graph, you see here voltage versus time graph, x-axis time, y-axis voltage, output is marked as HVL. HVL means high voltage level, means how much high it is. It is very much close to your power supply plus VCC. So if you apply plus VCC 12 volt, this will be 12 volt. If you apply plus VCC 15 volt, this will be 15 volt. So this is you have to remember, very simple. Whenever voltage at non-inverting input pin is greater than voltage at inverting input pin, we have taken 4 volt non-inverting, 2 volt inverting, output of op-amp will be high voltage level. Now the question comes here, how much should be this voltage greater than that voltage? So in case of op-amp, the difference in input voltage of 5 millivolt to 10 millivolt is sufficient to change the output of operational amplifier. So this you remember, only 5 millivolt to 10 millivolt. So if you write down the 5 volt in terms of 5 millivolt, if you want to write down 5 millivolt in terms of volt, I will write down 0.005 volt. 0.005 volt. So like that 5 millivolt is the term. Next, same op-amp is also used as a comparator, but now if you see here, voltage at inverting pin now greater 5 volt than voltage at non-inverting input pin. So in this case, whenever voltage at inverting input pin is greater than non-inverting pin, all of you know that output voltage of the op-amp will be forced to go into low voltage level, that is LVL. Again, the graph of time versus voltage versus time, y-axis voltage, x-axis time, output voltage will be below x-axis LVL. How much low voltage it will be? Equal to minus VEE. Means you apply minus VE as a minus 12 volt, it will be minus 12 volt. If you apply minus V as a minus 15 volt, it will be minus 15 volt. So simply you have to remember, voltage at inverting input pin is greater than voltage at non-inverting input pin, then the output is forced to go to LVL. And in this way, these two applications of the op-amp which we have already studied we have just revised. Now let us go to the next block. As I told you earlier, when we are using a potential divider circuit, R1 as upper resistor, R2 as a lower resistor, the junction point here we are calling as a X point. The voltage at that junction point is given by the formula Vx equal to R2 divided by R1 plus R2 into now here Vout, because for this potential divider circuit we are applying output voltage of the op amp as an input power supply to this potential divider circuit. So look at this diagram again. In this case, voltage at inverting input pin means positive pin is greater than voltage at non-inverting input pin means negative pin. Here V2 which is applied at non-inverting input pin is 4 volt. V1 applied at inverting input pin is 2 volt. Therefore, V2 is greater than V1. Voltage at non-inverting pin is greater than voltage at inverting pin. Therefore, output will be, look at the graph, output will be Vout is equal to high voltage level equal to plus VCC. Suppose now our plus VCC is 12 volt. If the plus VCC is 12 volt, then our output voltage of the op amp will be 12 volt as long as this is greater than that. So here, when this is a 12 volt potential divider circuit R1 and R2, in that case R1 if R1 is equal to R2, in that case our Vx is equal to, by using that formula, potential divider. So come here. In that case, if R1 equal to R2, then R2 suppose 1 kilo ohm, R1 R2 same 2 kilo ohm. So 1 kilo ohm divided by 2 kilo ohm will get cancelled, and Vout is equal to half of the Vin, means here in this case half of the Vout. So logic is very simple. Here is the Vout. So Vout is 12 volt. Therefore, I have written directly Vx equal to 6 volt for R1 equal to R2. Now, whenever we write this formula for potential divider circuit, this is the ratio of upper resistor divided by upper resistor to lower resistor plus lower resistor. This ratio will convert into one constant, and that is called beta. So see here. Therefore, I have written here beta equal to R2 divided by R1 plus R2. Therefore, here beta equal to R2 divided by R1 plus R2. If R1 equal to R2, then beta is equal to half. So it is very simple. So in this way here, that potential divider circuit, if you use over here, this voltage Vx is going to remain at plus 6 volt as long as this is greater than that. Voltage at non-inverting pin is greater than voltage at inverting pin. Now let us consider the opposite side also. Means now suppose voltage at inverting pin minus pin is greater 5 volt than voltage at non-inverting input pin. So all of you know that output of op amp, here look at the graph, will force to go into low voltage level equal to minus VE. So minus VE is also called as minus Vsat, plus VCC is also called as plus Vsat. So here now for this potential divider circuit is same, upper resistor R1, lower resistor R2, junction is X. So voltage at this point X is given by the formula is again same, but now output voltage is minus 12 volt, because minus V is equal to minus 12. So here see, if the output equal to minus 12 volt, then Vx is now minus 6 volt, not plus 6. It is minus 6 volt because output is minus 12 and potential divider circuit is same. Again we are considering R1 equal to R2. Therefore here this potential Vx is equal to minus 6 and beta is equal to R2 divided by R1 plus R2. So you can stop the slide, you can watch this slide, all information is given over here. Now this op amp along with this potential divider circuit is used in SCHMITT trigger. Now let us go to the next block, and suppose now here instead of applying a constant DC voltage, suppose if we apply a sine wave which is varying such that peak voltage is plus 12 volt positive peak and negative peak is minus 12 volt, and in that case sine wave which is applied to the inverting input pin and non-inverting pin, if it is grounded 0, then you know that output will be either plus Vsat or minus Vsat. Output will be either plus Vsat or minus Vsat. That depends on which half cycle is going on. Now forget about that. Let us concentrate on this now. Suppose if I remove this ground, what we'll do? We'll remove this ground, and at the non-inverting input pin, that is at positive pin, here we'll apply the output of potential divider circuit which I have just studied 2 minutes before. and that will be the diagram. Now here what will be the changes here? Minus terminal means inverting input terminal will apply the sine wave, but positive terminal, that is non-inverting input terminal, will be connected to the junction of potential divider circuit R1 and R2, and that is a very simple connection, and that diagram is called as diagram of inverting Schmitt trigger. So it is very simple. Let us go to that diagram. Yes, this is our diagram. What I told you, at inverting input pin, you apply the sine wave such that positive peak of the sine wave goes to Vp is equal to plus 12 volt, negative peak of the sine wave goes to minus Vp equal to minus 12 volt. See carefully over here. So sine wave is applied at inverting input pin. What about non-inverting input pin? The potential divider circuit, R1 is upper resistor, R2 is lower resistor. Only what we have done, we have taken this resistor horizontal instead of taking vertical, and the junction point is X point. Voltage at Vx is applied to non-inverting input pin, and this is the diagram of inverting Schmitt trigger circuit. Now here everything is same. Vx, voltage at a point X, equal to R2 lower resistor divided by R1 plus R2 upper plus lower into bracket close, into Vout. Here this output voltage of the op amp will work as power supply for this potential divider circuit. If R1 equal to R2, Vx equal to half of Vout. Beta is equal to R2 divided by R1 R2. Beta equal to R2 divided by R1 plus R2. Therefore, beta will come half as long as R1 is equal to R2. Therefore, as long as here at this point X Vx, the voltage will be decided by the output of the op amp now. If the output of the op amp is Vout is in plus Vsat, means plus VCC, that is HVL, then this Vx is equal to plus 6 volt. Or if the output of the op amp is in LVL, low voltage level, that is equal to minus VE, which is also called as minus Vsat, then this Vx is going to remain to minus 6 volt. So in this way, voltage at a point X here now depends on magnitude of output voltage of the op amp. If the output voltage of the op amp is in HVL, this Vx is plus 6 volt. If the output voltage of the op amp is in LVL, low voltage level, and we have considered here, see, minus V equal to minus 12 volt plus VCC equal to plus 12 volt. Supply applied to the op amp we have mentioned very clearly. Therefore, when we say Vout is equal to HVL, it will be equal to plus 12 volt. When we say Vout equal to LVL equal to minus 12 volt, and in this way here Vx will go on changing from plus 6 volt to minus 6 volt. Now let us understand the working principle or working of inverting Schmitt trigger. So in this case here, first of all, we have to consider that. So let us consider the output voltage of the op amp initially will be in high voltage level. Output voltage of the op amp initially will be in high voltage level. Now why we consider that? There is one logic. When we make the connection somewhat like this, and when we apply the sine wave over here, sine wave will start from 0 volt. Sine wave will start from 0 volt and it will go to plus 12 volt. But the moment as soon as you turn on the power supply, this voltage is 0 volt, means voltage at inverting pin is 0 volt, and there is some output voltage which is called offset voltage, output offset voltage of op amp present at the output, and because of that some output offset voltage of the op amp, here some voltage comes in millivolt. At Vx point some voltage comes in millivolt. Therefore this is 0 and this is some millivolt, and therefore initially output of op amp is forced to go to HVL, and that is what we have to consider in this diagram. The moment as soon as you make the connection and you turn on the power supply, the output of op amp is forced to go to HVL. So here I have written inverting Schmitt trigger. Initially the output of this circuit is considered to be in HVL into bracket reason. What is the reason? Due to output offset voltage. Due to output offset voltage. So here, due to some output offset voltage, this voltage in millivolt will get divided, no doubt. But we want only 5 millivolt over here. So here we want only 5 millivolt greater than the 0. Then output of the op amp will be forced into HVL, and that is what we have to consider. Now, when you consider output voltage of the op amp is equal to HVL is equal to plus 12 volt, Vx will be 6 volt. Vx will be 6 volt. And now this point will be at 6 volt. Now let us see how long how long time it remains in 6 volt, because our sine wave, we have turned the circuit on and our sine wave started increasing the voltage from 0 volt to 1 volt, 2 volt, 3 volt, 4 volt, and like that I have marked here the point, midpoint it is called of the Vp, because Vp is 12 volt. So half of that will be 6 volt. So unless and until the voltage at inverting pin, which is increasing voltage of the sine wave, does not crosses the 6 volt level, the output of the op amp will be maintained at HVL, high voltage level. So this is very simple understanding, and with the help of graph we are going to show you that in the beginning, unless and until the output of inverting pin does not crosses the 6 volt, the output of the op amp is maintained at high voltage level. Let us go to that graph. This is the symbol. So this is entire circuit of inverting Schmitt trigger, and this is the symbol of inverting Schmitt trigger. Look at the symbol triangle, because we are using op amp, and this is the hysteresis sign and not gate. So because we are applying the input at inverting input, that's why it is a inverting symbol. And this will be the hysteresis loop, which we are going to study after completing the derivation of the op amp as inverting Schmitt trigger. Now look at this diagram. This diagram is self-explanatory. Everything is given very clearly. Here is the sine wave. X-axis time, y-axis voltage. This input voltage goes on increasing in positive half cycle from 0 volt to Vp equal to 12 volt. Then decreases, comes to 0. Then goes in negative half cycle. So in negative half cycle when it goes minus Vp equal to minus 12 volt. Everything is written here. So sine wave is varying such that 0 volt to plus 12 volt Vp, then 0 volt, then again 0 volt to minus 12 volt. Now look at this output. This is the output of the inverting Schmitt trigger, that is the output of the op amp. So here, unless and until the inverting input terminal does not crosses 6 volt, means up to 6 volt of the sine wave, at the output we have considered high voltage level. This is the blue line. So it is HVL equal to plus 12 volt. So for the time from 0 volt to 6 volt, the output of the op amp remaining in high voltage level. So here let us go again to that diagram, and you will understand that in the beginning we have considered this output voltage as a high voltage level. Therefore, high voltage level is equal to 12 volt, and potential divider circuit converts that 12 volt into a 6 volt at a junction Vx. So here non-inverting input voltage will be at 6 volt. But as soon as you turn on the circuit, the sine wave applied at inverting input pin and the voltage at the sine wave starts increasing from 0 volt to 6 volt. As soon as this crosses 6 volt, this voltage becomes greater than 6 volt over here. And therefore, whenever voltage at inverting pin is greater than voltage at non-inverting pin, the output of the op amp changes from HVL to LVL, and it goes in LVL, which is shown in that graph. So let us come see here. From 0 volt to 6 volt, output of op amp Vout is in HVL. As soon as inverting voltage pin crosses 6 volt, means voltage at inverting pin becomes greater than voltage at non-inverting pin, the output of the op amp, look at here, the output of op amp, therefore this point is called upper trigger point. Upper trigger point, UTP. This point is called upper trigger point. At exactly at a 6 volt or just above the 6 volt, HVL changes its state and goes to LVL. That is LVL equal to minus 12 volt, because we have taken plus 12 and minus 12 as a supply. Now as soon as the output of the op amp goes to LVL, what happens? As soon as the output of the op amp, when input at inverting pin crosses 6 volt, output will go to LVL, means minus 12 volt. So when output goes to minus 12 volt, Vx will not be plus 6 volt. Vx will not be plus 6 volt. Vx will become minus 6 volt. And in this way now, this is minus 6 volt and this inverting input pin is now at 7 volt, 8 volt, 9 volt, 10 volt, 12 volt. So this is greater. Therefore, Vout will continue to remain in LVL, low voltage level. Now we want to see that how long time LVL remains at the output. Now one thing is very clear, when output of the op amp change from HVL to LVL, the Vx is minus 6 volt. Vx is minus 6 volt. Now as soon as Vx becomes minus 6 volt, the voltage at inverting pin is increasing such that 7 volt, 9 volt, 12 volt. Then it will come down to 11 volt, then 10 volt, then 6 volt. But still see here, it is a minus 6 and it is plus 6. So plus 6 is greater than minus 6. The output of the op amp will continue in LVL. And even though it comes below 6, say suppose 4 volt, 3 volt, 2 volt and 0 volt. So even though the voltage at inverting input pin is 0 volt, non-inverting input pin is at minus 6 volt. Therefore 0 is greater than minus 6 and output will continue to remain in LVL. Now let us go below 0, minus 1, minus 2, minus 3, minus 4, and this is the point which I have marked here. At that point, this point is minus 6 volt, and exactly at this minus 6 volt, here again minus 6 volt. So both are minus 6 and minus 6. Therefore, output of op amp will go in 0. So this is the crossing point, and that is called LTP, lower trigger point. UTP, upper trigger point. LTP, lower trigger points here. So when it is crossing minus 6 volt, just below minus 6 volt, when the voltage at inverting pin goes just below minus 6 volt, then you compare here, when the voltage at inverting input pin just goes below minus 6 volt, then it's minus 6.1 if you say, and if you compare minus 6 volt with minus 6.1 volt, so minus 6 volt will become positive because minus 6.1 volt is more negative. In this way, as soon as the inverting voltage crosses or goes just below 6 volt, minus 6 volt, the output of the op amp will again change from LVL to HVL. And then here you see here, from this point onwards, your output of the op amp will force to remain in high voltage level. And as soon as this goes in high voltage level, you will understand that high voltage level equal to plus 12 volt, and this voltage at point X will become plus 6 volt. So here now you can see the graph very clearly. As soon as the voltage at inverting pin just goes below minus 6 volt, the output of the op amp will change the level from minus 12 volt to plus 12 volt, high voltage level. And how long time high voltage level is maintained? Now, unless and until the output, unless and until the output will not go in LVL. But how, when it will go in LVL? Now we'll see from the graph again, diagram. See here, as soon as the output goes to HVL, this becomes plus 6 volt. Now here the voltage is going on decreasing, 7 volt, minus 8 volt, minus 9 volt and minus 12 volt. So here this is a plus 6 volt. So even though it is a minus 12 volt at this point, minus 12 and plus 6 if you compare, plus 6 is greater than minus 12 volt. Therefore, output will continue to remain in HVL. Then after minus 12 volt, what happens here? The output starts decreasing in negative direction. Then minus 12, minus 11, minus 10, minus 9, minus 5, and say suppose minus 1 and then 0. So when this voltage is at 0 volt, here it is a 6 volt. So definitely 6 volt is greater than 0 volt, so output will continue to remain in HVL. Let us go further. When this will cross 0, then it will come to 1 volt, 2 volt, 3 volt, 4 volt, and like that. Exactly at plus 6 volt, both voltages will become same, and the output which was in HVL will become 0. Output which was in HVL will become 0 when exactly at plus 6 here. So crosses 0, plus 1, 2, 3, 4, 5 and 6, plus 6. Exactly at plus 6, output which was HVL will become 0 here. And when this voltage just crosses 6 volt, output will go in LVL like this. So below 0 it will go LVL. And in this way here, I hope you have understood that in the beginning there is HVL, but later on when the input crosses the plus 6 volt, the output goes to HVL to LVL. And then circuit will go on continuing accordingly, and at the output either HVL will be there or LVL will be there. So in this way, this is called working of inverting Schmitt trigger. Working of inverting Schmitt trigger. Here we have considered R1 equal to R2. You can change the value of R1 and R2. If you change the value of R1 and R2, what will happen? Vx will change. Vx will change, and Vx is very important playing roles here. Vx is 6 volt, therefore upper trigger point is at 6 volt. Vx is minus 6 volt, therefore lower trigger point is at minus 6 volt. But if you change the value of R1 and R2, UTP and LTP will change, and this is very important for hysteresis, because hysteresis is nothing but the difference between voltage of upper trigger point and voltage of lower trigger point. So hysteresis width can be increased or hysteresis width can be decreased. That you will come to know from the graph I am going to explain you. See here, for example. See, this is hysteresis. So this is hysteresis is a graph of y-axis also voltage and x-axis also voltage. So this is very important thing in hysteresis, because normally we do plot the graph on y-axis current, x-axis voltage, or y-axis voltage, x-axis time. But hysteresis is having on y-axis voltage and x-axis also voltage. So what is on y-axis? On y-axis voltage output means output voltage of the op-amp, either plus Vsat here, either plus VCC or minus Vsat means minus VE. So it is having only two values, plus VCC and minus VE. So this thing is not under your control. So you can say it is plus VCC and it is minus VE. But under your control is what? This width. And hysteresis, this width is there. So this is upper trigger point. So here it is 0. So if you say it is at plus 6 volt, then lower trigger point will be at minus 6 volt. If you say this is as a plus 1 volt, this lower trigger point will be at minus 1 volt. And this width can be changed. And who decides this width? The component R1 and R2 decides this width. So that is a very important factor in this case of the Schmitt trigger. And what is the symbol of Schmitt trigger? The symbol of inverting Schmitt trigger is like this. Now, here is the hysteresis again. Same thing. Either output will be Vsat plus or Vsat minus. There is no change in the output of the op-amp, but you can change the width of hysteresis. So value of R1 and R2 are very important because that decides the Vx, and Vx decides upper trigger point and lower trigger point. UTP means upper trigger point and LTP means lower trigger point. Trigger means what? Output of op-amp changes from plus 12 volt to minus 12 volt, HVL to LVL, or vice versa. Output of op-amp changes from low voltage to high voltage. So I hope this you understood. Now we'll proceed for the derivation of. Now here one more thing you see here. The application of Schmitt trigger inverting bubble sign is there, and this is the hysteresis graph. So here if you apply the square wave which is having a positive edge little bit incline and negative edge also little bit incline. So what the Schmitt trigger circuit does? Schmitt trigger circuit gives the proper shape, means this incline will come exactly perpendicular. this incline will come exactly perpendicular. But remember, HVL will become LVL and LVL will become HVL because it is inverting Schmitt trigger. It is a inverting Schmitt trigger. So this is one of the important application of this thing. Now in this diagram, the Schmitt trigger is working on plus 5 volt supply with respect to ground, and there are so many ICs which I am going to show you. IC of the Schmitt trigger which is working as single power supply, IC of the Schmitt trigger which is working on dual power supply, and accordingly. So now I think so you understood this. Now let us see the what derivation for hysteresis voltage. Hysteresis voltage is given voltage V and H for hysteresis. So it is very simple. Now you know that in the Schmitt trigger circuit, which is called inverting Schmitt trigger circuit, Vx is the voltage, and this Vx very important for deciding upper trigger point UTP and lower trigger point LTP. Therefore, when we are going to derive hysteresis voltage VH, we start from the formula of the Vx, and it is very simple. It is a potential divider circuit. So let us start for the hysteresis voltage. So Vx is equal to, all of you know very well, R2 divided by R1 plus R2. R1 plus R2 I have taken into the bracket, and here R2 divided by R1 plus R2. One more bracket I have put into Vout. So this is our voltage at a point X potential divider formula. Very simple. Now we have considered that beta is equal to R2 divided by R1 plus R2. So here, instead of writing every time this R1 and R2, we will write down beta. So Vx is equal to R2 divided by R1. Instead of that, what will come? Beta into Vout as it is. Into Vout as it is. Now you know that what is Vout? Vout is the output of the op amp. Output of op amp will be either in plus VCC or minus VE. Plus VCC we called as Vsat plus, and minus VE we called as a Vsat minus. Therefore Vx equal to beta into Vout. Instead of that, what we can write, Vx is equal to beta into star is into Vout means plus Vsat, or you can say that Vx equal to beta into plus VCC. Similarly, you can say that, or Vx equal to beta into, because this output will be neither in permanent HVL or nor in LVL, therefore sometime HVL, sometime LVL. So Vx equal to beta into minus Vsat, or you can say that Vx equal to beta into minus VE. So output of the op amp will changes from HVL to LVL. HVL equal to plus VCC, which is also called as Vsat plus. LVL equal to minus VE, which is also called as Vsat minus. So it is very simple. In inverting Schmitt trigger, initially output is in HVL. So that is what already I have told you. In inverting Schmitt trigger, the output is initially in high voltage level. Therefore, VUT means upper trigger point voltage. Therefore, VUT means upper trigger point voltage is equal to beta into plus Vsat. VUT means upper trigger point. When the triggering happens, when the output will change from HVL to LVL, the output will change from HVL to LVL at beta into Vsat plus. So here beta is our half, and Vsat plus is 12 volt, means 6 volt. Means plus 6 volt is our upper trigger point. And what is lower trigger point? Exactly same, but here instead of plus Vsat it will be minus Vsat. So VLT means lower trigger point. Lower trigger point. If the output is in LVL, when the output goes to HVL, so that is called lower trigger point. So if the output is in LVL, then when the output goes to HVL, so that is your beta into minus Vsat. So minus Vsat is what? Minus 12 volt. Our beta is half because we have taken R1 equal to R2. So lower trigger point is our minus 6 volt, and that we have studied from the graph also. Upper trigger point and lower trigger points here. Upper trigger point is plus 6 volt, lower trigger point is minus 6 volt. So very simple thing. Start from Vx. You know Vx is this. Vout can be HVL or LVL. HVL means plus VCC, LVL means minus V. So in this way you put that, and we'll use the plus Vsat and minus Vsat. And then you know that upper trigger point is beta into Vsat plus, because initially the output of op amp of non-inverting Schmitt trigger is in high voltage level. Therefore upper trigger point is beta into plus Vsat. Here this VUT in case of inverting Schmitt trigger, which we are going to study after some time. So this VUT in case of non-inverting, not inverting Schmitt trigger will come what you know, beta into minus Vsat, because in case of non-inverting Schmitt trigger, output will be initially in low voltage level. Output will be initially in low voltage level. We'll come to that later on. Now let us go to the next step. So this is very simple. But hysteresis voltage VH. What is a hysteresis voltage? VH equal to voltage of upper trigger point. Okay, voltage of upper trigger point minus voltage of lower trigger point. So hysteresis voltage is nothing but voltage of upper trigger point minus voltage of lower trigger point. As I told you, hysteresis is a graph of x-axis and y-axis, and in this graph only, on y-axis there is a voltage, and on x-axis again there is a voltage. On y-axis, output voltage, that is voltage of op-amp, which always remains in plus Vsat, that is plus VCC, or minus Vsat, that is minus VE, and this width, that is here this point is marked VUT, means upper trigger point voltage. Here this point is marked VLT, lower trigger point voltage. Now why left hand side LT and why right hand side UT? Because this is your vertical axis, that is y axis, this is horizontal axis, this is x axis, center is 0. So upper trigger point will be in, yes, upper trigger point will be positive and lower trigger point will be negative. That's why this is on the left hand side and this is on right hand side. So in this way you can understand this very well. The width of hysteresis can be changed by changing the voltage at a point x. So now let us come to the hysteresis voltage. VH equal to VUT minus VLT, and you know the equation for VUT, you know the equation for VLT, and it is very simple. VH equal to, if I write down VUT upper trigger point as a beta plus Vsat and minus VLT as a beta into minus Vsat. So here beta I will take common. Beta I will take common. Then in bracket what remains? In bracket plus Vsat remains. Minus, here it is the minus. Into bracket it will be minus Vsat. Minus Vsat. So this is a very simple mathematics. VH equal to beta I have taken as a common. So here plus Vsat comes, because it is a difference of VUT and VLT, so minus sign is there, and into bracket this minus Vsat will come here, bracket close, and one more bracket. Now it is very simple, Vsat minus into bracket minus Vsat, so minus minus will become plus, so this is plus Vsat, and in this way here this plus Vsat and this plus Vsat I have taken as a 2 Vsat, and that 2 will come over here. So here Vsat plus minus minus will become plus, and again Vsat. So plus Vsat plus Vsat, that will become 2 Vsat, and this is the VH equal to 2 beta into Vsat. But beta is equal to R2 divided by R1 plus R2. In the beginning only we have taken, instead of writing R2 divided by R1 plus R2, we'll write down short form as a beta. And here if you substitute that value, VH equal to 2 into beta, 2 into beta, so that will come somewhat like that. See here, VH equal to, here we have to substitute 2 as it is, beta. What is beta? R2 divided by R1 plus R2. So here I have written R2 divided by R1 plus R2, bracket complete, into, here into Vsat plus, or same equation you can write down. Somebody feels that I want Vsat first, so Vsat will come here first, into 2 times of R2 divided by R1 plus R2, 2 times of R2 divided by plus R1 plus R2, and in this way here this is a very simple equation for the hysteresis voltage and derivation. Now in today's lecture what I will do, I will conclude that the inverting Schmitt trigger is understood by you, and now to observe this hysteresis voltage on CRO, what care is to be taken, that I will explain you in short, and then in the next lecture we will proceed for non-inverting Schmitt trigger. So here let us go now for observation of, you can say that, Yes. So here you know that you are applying the input as a sine wave. So sine wave you observe on CRO. You know that the square wave is the output of what? Operational amplifier. It is sometime HVL, it is sometime LVL. Now you have two inputs. You have one input as a sine wave and one output as a square wave. Means you have two signals. One is sine wave as an input signal and square wave as a output signal. Now our target is what? How to observe the hysteresis loop on CRO. So this hysteresis loop on the CRO looks like this. So you see this. So here, this is the width of the hysteresis. This is the width of hysteresis voltage, you can say. This is either this is plus VCC and this is minus V. So HVL and LVL we cannot control. It is depending on the supply of the op amp. But width of hysteresis you can control by controlling the voltage at a point X. And voltage at a point X can be controlled by changing the values of R1 and R2. Now to observe this type of waveform on CRO, what is to be done? That I am going to explain you in short. You have already input signal as a sine wave. You have output signal as a square wave. So what you do, you apply the input sine wave at a channel 1 and output square wave at channel 2. You apply input sine wave at a channel 1 and output square wave at channel 2. See here, channel 1 input I have given as a sine wave, channel 2 input you can given as a square wave. You can change also, no problem. So here, to observe the hysteresis loop on CRO screen, apply sine wave at channel 1 and square wave at channel 2 and keep the position of holds per division knob of both channel at same, because channel 1 is having 1 holds per division knob, channel 2 is having another holds per division knob. So both holds per division knob should be at the same voltage, say 5 volt per division, 10 volt per division, whatever. If it is in 5 volt per division, it should be in 5 volt per division accordingly. Okay. Now see here, next, volts per division of the both channel at the same voltage level. After doing this, you will get sine wave as well as square wave on CRO, because your CRO is dual channel. You applied sine wave at X channel, you applied square wave at Y channel or channel 2, then you will get sine wave as well as square wave. Now to observe the hysteresis, very important thing what has to be done, press the XY mode knob as shown below. Means I have shown the diagram. Press the XY mode knob. After pressing the XY mode knob, you will observe this type of the hysteresis loop. And after pressing the XY mode knob, when you vary the Y position of one channel, this will get elongated. Therefore, I told you to keep both the holds per division knob. When you change the holds per division of any one channel, this will get elongated. So in order to avoid that, holds per division knob of both the channels should be at the same voltage level. Then now when you press the XY mode, where is the XY mode here? See, this is our CRO. You applied sine wave here, you applied square wave here. This is the channel 1, this is the channel 2. You kept the holds per division knob at the same level. So you have to keep it here. If it is not same, you have to keep that in the same holds per division knob. And XY mode knob is here. See here, I have written arrow. X dash Y. XY mode push to on switch. It is a push to on switch. So you have to press the XY mode knob. As soon as you press the XY mode knob, already you have applied sine wave here, already you have applied the square wave here, already you kept both hold per division knob at the same voltage. As soon as you press the XY mode is very must, you will observe this type of the waveform. And this is called as hysteresis loop. This is called as hysteresis loop. Otherwise, it is very difficult to observe the hysteresis loop. If you don't press XY mode knob, CRO must be forced in XY mode knob. And when you force the CRO in XY mode, remember that X channel, time per division knob get disabled. Time per division knob gets disabled. So I have written here remark. Don't worry about the time per division knob because it is now disabled. As soon as you press the XY mode, CRO forces into the XY mode and time per division knob is disabled. So you can only change the volts per division knob, keep both the volts per division knob at the same voltage level, and you will observe hysteresis loop on CRO. So hysteresis loop on CRO is somewhat like this. And this is what in graph we represent it like this. In graph we represent it like this. So this is hysteresis. This is under not your control. On y-axis output will be either Vsat plus, that is HVL, and either Vsat minus, that is LVL. But this width of hysteresis is under your control because you have designed the circuit. You have designed the circuit such that R1 and R2 decides this voltage. And one more circuit is there, which is again the same thing, but they have mentioned Schmitt trigger using op amp. Again, it is inverting Schmitt trigger. Instead of showing the sine wave, they have shown the signal generator over here, which is very simple, a sine wave signal generator applied through the R. But remember, output is applied back to input non-inverting with the help of R1 and R2 as a potential divider. And here we have marked the arrow and shown that this point is the point which controls upper trigger point voltage, lower trigger point voltage. So this is the voltage which is decided by you people by changing the values of R1 and R2. Today in our lecture we have taken R1, R2 same, plus VCC 12 volt minus V equal to minus 12 volt. Therefore our upper trigger point is plus 6 volt and our lower trigger point is minus 6 volt. So this is the point where you can change that. Now the same diagram is over here, but in this diagram it becomes very difficult to understand the change in the levels. Here it is very small square wave. Can you see here plus Vsat, and for a very small time it is remaining in HVL. So here it is UT, upper trigger point voltage. It is LT, lower trigger point voltage. Can you see here? And 1, 2, 3 points mark here, 1, 2 points mark here. The arrow is shown, and this is called tripping points. Means at this point the triggering happens. Triggering means changing in the voltage level of the op amp from HVL to LVL or vice versa, LVL to HVL. So this graph is also very simple, but this graph is very much, you can say that, condensed or compressed graph. So here the change in the voltage level from HVL to LVL in the beginning. In the beginning, the output of inverting Schmitt trigger is in HVL. So here for small time HVL is there. Can you see here the arrow? And then it goes to LVL. From this point, upper trigger to lower trigger point, the output will continue to remain in LVL. Then from this point, lower trigger point to upper trigger point, output will remain to continue in HVL. So this is given over here. So to avoid these complications in understanding the compressed graph, I have drawn a pent graph, and from this pent graph you can understand that from this point to this point, so this is plus 6 volt which we call upper trigger point, plus 6 volt, and this is minus 6 volt which is called lower trigger point. So it is over here, and I hope this graph will give you the better understanding. From this 0 to 6 volt, this is in HVL, HVL equal to plus 12 volt. So this I have just little bit elongated along x-axis, and in this way your derivation for the hysteresis is again a very same, very simple. Vx we have to take into consideration. Consider beta is equal to like this, then Vx is equal to beta into Vout, but Vout cannot be in HVL or in LVL, so it will be either HVL or LVL, that is plus VCC or minus VE, plus VCC called plus Vsat, minus VE called minus Vsat. In case of inverting Schmitt trigger, output is in HVL, therefore upper trigger point will be beta into plus Vsat. In our case it is plus 6 volt. So here upper trigger point is beta into plus Vsat, lower trigger point will be opposite of that, beta into minus Vsat, and hysteresis voltage is the voltage along x-axis, that is the width. Hysteresis voltage is the difference between upper trigger voltage VUT minus lower trigger voltage. Substitute the value and finally you will get the derivation for hysteresis voltage. I hope you have understood the concept of inverting Schmitt trigger. This is the symbol of inverting Schmitt trigger. HVL will be converted into LVL, LVL will be converted into HVL, and proper shape will be given. So in this way, this is again one more small symbol of the inverting Schmitt trigger. So bubble sign is marked, that is inverting Schmitt trigger, because we are applying the input sine wave to the inverting input terminal, and this is your hysteresis graph. So in this way, I will conclude that today we have completed only inverting Schmitt trigger, and this is the diagram of the inverting Schmitt trigger. Thank you very much for watching the video. You can watch the video again and again and you can get understand the concept of inverting Schmitt trigger. In the next lecture, we'll complete non-inverting Schmitt trigger and derivation for hysteresis voltage of non-inverting Schmitt trigger. So non-inverting Schmitt trigger is also very simple. As the name suggests, non-inverting, the input sine wave is applied at non-inverting input pin, and how it is done that we'll see in the next lecture. So thank you very much for watching the video. See you in the next lecture for understanding of non-inverting Schmitt trigger. Thank you.